Thank you all for being here. I know it's the end of 2 long days, so appreciate this. This is also going to be an academic talk, so when relevant stuff comes up, I'll make sure to highlight it in case you're checking email or things like that. That's okay. And hopefully this will be fun. This is very much a research prototype that I'm going to describe. I would love to see it running on petabytes of data. My goal here is to highlight what we think is an interesting research problem, describe some of the techniques that we've developed, and talk to you about some of the results that we got. So I'm Manasi. I'm a PhD student in the database group. I heard Mike's name a lot. He and Sam lead the database group at M.I.T. This work is joint work with Sam, Aditya from UIUC, and Alkis, who's now at Google. All right. So why do we care about visualization? If you looked at all the talks over the last 2 days, visualization was a key component of all the stacks. Either it came at the beginning as a first step in analytics, or it came at the end while you were reporting results to the marketing department or bosses and so on. In this talk, I will be focusing on visualization as a tool for analysis. So suppose that you're an analyst who's looking at census data. This data has things like age, education, marital status, sex, race, income, so on. And let's call the number of attributes in this table as A. And the task that you're assigned is, well, tell me something interesting about the socioeconomics of adults who have never been married. So when you think about this, you might wonder, oh, do people who have never been married, are they more educated than people who have been married? Do they make more money? There might be hypotheses that you want to test. The first thing that you will probably do is start building some charts. You want to get a feel for the data. What's the range of the data? Are there outliers? What trends exist? And so on. So this is a popular kind of chart you might make. It's a histogram. It's just showing you the number of adults with various marital statuses. And in sort of O notation, the number of histograms that you could build would be O of A. And if you now consider multi-attribute histograms, it is an exponential space. Another kind of chart you might want to build is scatter plots. These are very efficient at showing you trends and correlations that might be harder to spot otherwise. Again, there's a lot of scatter plots that you might want to construct. This is yet another view. It's an aggregate view. And this is showing you the average capital gain for adults falling into various categories. And this might be helpful if you want to compare average capital gains across various categories. And finally, let me point out one other kind of visualization which will be relevant moving forward is a kind of comparative visualization. So you're looking at adults who are married and adults who are not married, and maybe the comparison between those two is the one that has the most insights in it. So this is a really long-winded way of saying there's a lot of visualizations that you can make. Some of these would be interesting, a lot of them probably not. So how can we help the data analysts to get to their insights faster? Well, instead of showing them all these data, all these visualizations, maybe we can pick the ones that are most relevant for the data and for the analysis task that the analyst is doing. And that is what SeeDB does. SeeDB is what we call a visualization tool, a visualization recommender. So a lot of people here are familiar with Tableau, maybe Spotfire, and other tools in that category. Imagine this thing as a component that as you're analyzing your data, depending on what view or what subset of the data you're looking at, it tells you what trends might be interesting to look at, and it does so automatically. So our hypothesis is that this can make the analysis process a lot faster and expose the user to trends that they otherwise would not have tried. So there's been a little bit of related work, a bunch of visualization tools. Tableau and Spotfire actually have introduced some sort of recommendations, which are essentially rules of thumb for constructing good visualizations. So in case you're looking at a time series data, this is how you should visualize it. Or if you have a small number of distinct values, this is the right way to visualize it. A lot of research has recently been coming up in the space, like VizDeck, Profiler, Voyager, which try to find interesting insights automatically. Interestingly, the closest work that I can think of is Scagnostics, which goes back to Tukey, the famous statistician. What he did was to come up with a set of metrics that determine the utility of scatter plots. So our work builds on some of these ideas, but we're applying a very different utility metric that I will talk about now. Okay, we're in the business of recommending visualizations. So there are two things that we want to answer. The first one, how do you define relevance? I'll call that utility. And secondly, how do you do this efficiently? We want this to scale to a large number of rows. We want to avoid the curse of dimensionality, which is sort of a necessary evil here. And we want to do this at interactive timescales, because this is visual analytics. You're not going to wait for 5 minutes in order for your query to run. So let's tackle the first one. When you think about what makes a visualization interesting, you can come up with a host of answers. It is, well, the data distribution, the query, which is what am I trying to answer, what's the metadata like, what's the schema, the number of distinct values, and so on. There's also context, which is, as an analyst coming in, I have some hypotheses in my head, and I'm trying to figure out whether the data proves or disproves them. And finally, we have user preferences and aesthetics. In this work, we focus on the first three, which is data, what does the distribution look like, query, what subset of data are you interested in, and metadata. You might wonder why, because, well, you could make a really complicated utility metric. And the reason is that we think data captures a significant part of user interest, not all, but a significant part. You also don't need any external data. And finally, if you're thinking of, oh, I can build an ML model which can learn user preferences, you have no data at cold start, so you need to leverage other sources of information in order to provide recommendations. So that's how we're defining utility. I'll get to the actual formula in just a sec. Okay, so we're limiting ourselves to bar charts and aggregate visualizations in SeeDB. We hope to extend to scatter plots in the near future. And we think that this is a good place to start, because as your data grows, aggregates are essential. You cannot look at every row one at a time. And scatter plots can get overwhelmed when you have a lot of data. We also find that a large fraction of common visualizations are actually bar charts. And again, if you looked at any of the visuals that were presented at this conference, most of them were bar charts. Since you're building a bar chart, you can represent it very easily, which is 3 components. What is the x-axis? That is what you're grouping with respect to. What is the y-axis? The thing that you're measuring. And are you applying an aggregate function? So we're limiting ourselves to aggregates that are sort of SQL-friendly aggregates, let's say, like count, average, sum, and so on. And coming from a database group, we love it when we can transfer things into SQL queries. So anytime you want to build such a chart, you can write it as a SQL query that's just select the dimension, apply the aggregate to the measure, group by the dimension, and apply any selection predicates. So that's how we're building these visualizations. All right, so now comes the crux of the issue. What makes the visualization interesting? So let's go back to Tukey, because he has really great quotes in this area. And one of his really famous quotes is, "The greatest value of a picture is when it forces us to notice what we never expected to see," which is another way of saying what is surprising or what deviates from expected trends is interesting. And that's our premise. So if the visualization shows something unexpected, then we want to surface that visualization. So let's be very concrete and figure out what that means for the kinds of charts that we're building. This was our example. We're looking at the census data set where marital status is never married. Your dimensions are race, work type, sex, etc. The measures are capital gain, capital loss, and other numeric attributes. And there are a few aggregate functions. So in order to figure out whether something is surprising, you first need to know what you expect the visualization to be. And then you can determine if the visualization you saw is actually interesting. So if you were interested in seeing how race varied, how average capital gain varied with race, you might run this particular query. What this is doing is this is producing an expected trend of average capital gain versus race. Notice that this is for all adults. This is not only for non-married adults. You might get a chart that looks like this, and we call this the expected distribution. This is the trend that you expect to see. Now we can actually go and we can find what trend you're actually seeing in the data set that concerns you. So we run the same query again, except we run it on the subset of data that we're interested in. So this gives you another bar chart, and we call this the actual distribution. So the only difference is that you're running the query on a subset of data versus you're running the query on the entire data set. The great thing is that we now get a comparative visualization. So now we can say, oh, well, how do adults who have never been married compare to the entire population? And since our premise is that deviation is interesting, we define utility as the difference between these two probability distributions. And you can choose your favorite distance metric here. It could be Earth mover's distance, L2, or something more complicated. So that's how we're computing utility. Deviation is interesting to us. We want to rank visualizations based on deviation and surface the ones with highest deviation. So this is an example of a low utility visualization. The red and the blue bars look essentially the same, and therefore we aren't terribly interested in it. This visualization shows significant differences between the two populations, and therefore we surface it as a high utility visualization. So that's the part where we define what is interesting to us. Now let's move on to some of the more systems building aspects of it. How do we make these recommendations efficiently? Our architecture is pretty simple. We made the decision of sitting on top of the database because we wanted SeeDB to be able to run with row stores, column stores, in-memory stores, whatever you would like. And all the data processing is delegated to the DBMS. So just to give you a sense of the space that we're looking at, if you have D dimensions, M measures, and F aggregate functions, the number of potential visualizations is their product. The number of queries you issue to the database is on the same order. We can also assume that each query is potentially going to scan the entire data set, making this very, very inefficient. Another thing that we need to keep in mind is of the hundreds of views that you could construct, your only concern would say the top 10 or top 20 of them. So you're wasting computation on the remaining 80. And we want to find ways to mitigate that. So we have two goals. We want to get interactive or near interactive latencies. We also don't want to waste resources on bad views. And we developed two strategies to make the recommendations efficient. The first one is runtime pruning, which essentially means as we look at visualizations, let's throw away the ones that are unlikely to be interesting, and let's focus on the ones that are high utility. And the second one is more traditional, rather simplistic multi-query optimization, where instead of running hundreds of queries, we combine them in interesting ways to reduce the total number of queries. So I'll give you a brief overview of both of these and then get to the evaluation. Like I said before, we want to identify views with low utility early on, and then we want to throw them away. And you can do so quite easily by using estimates that are based on samples. And the way that we select samples is a little bit interesting, and I can talk about it offline, but I'll give you the gist of what we're doing. We use two different techniques to do pruning. One is confidence interval-based pruning, which I believe a lot of people here would be familiar with. You have confidence intervals on the estimates of utility, and you throw away visualizations based on these intervals. And the other one is multi-arm bandit pruning, which I will talk about next. So multi-arm bandit is a very weird name for a very sort of interesting problem setup. So there, you have a gambler who is faced with a set of slot machines. And every slot machine has an underlying reward distribution. So the R's are actually distribution functions. They're not a single value. And the question you're trying to answer is which machines to play and in what order to maximize the reward. So this guy wants to get as much money possible. He wants to figure out how to game the system. So the way that the algorithms work in this case is you draw from the distributions of each machine. So you play a machine, you draw something from that distribution, you get an estimate of that reward distribution. You do so for another machine, and you keep continuing until you get estimates for the entire set of slot machines. And depending on what you're trying to optimize, whether you're trying to optimize maximum reward, or you're trying to find the slot machines with highest distribution, highest reward, highest mean rewards, there are various algorithms you could use to determine your strategy. In our case, we have a very similar setup, except we don't deal with slot machines. We deal with visualizations. So we have a set of visualizations with underlying utilities. And our goal is to find the views with maximum utility. What we do is very similar. For a sample of data, we can compute the utility of that particular visualization, which gives us an estimate small u1. We can do the same thing for all the other visualizations and get estimates for the entire set of visualizations. Finally, the way that we prune these is by using a technique that is called successive accepts or rejects. It essentially entails ranking the views by utility. There are some special differences that you compute, and depending on the size of those differences, you either accept the highest utility view as being in your answer, or you throw out the view with the lowest utility. So that's generally the technique that we're using. In the evaluation, I'll talk about how well it does and some latency effects of doing this pruning. So we've come up with a few ways to throw out low utility visualizations. But we still need to execute a bunch of queries in order to get these estimates for utilities. Remember that each visualization is 2 SQL queries. So if you run this sort of the naive way, you can spend hundreds of seconds trying to evaluate all of these visualizations. And we ran these experiments on both row stores and column stores, but that won't be the focus of the results that I'm discussing here. So latency greater than 100 seconds is clearly not acceptable. So our goal is to minimize the number of queries and scans that we perform. For this, we adopt 4 optimizations, which are sort of simple but effective optimizations. We combine the aggregate queries that we run on the subset of data and the full data set. We combine multiple views with the same dimension but different measures. So instead of computing average of profit and average of sales in 2 different queries, you can combine them into one. You can also combine multiple group-bys. And I'll get into this in a minute because it's not as straightforward as it might seem. So instead of grouping by race separately and grouping by gender separately, you could group by race and gender at the same time. And then finally, you can use parallel query execution. So what's interesting about grouping multiple group-bys? If your query has a single group-by, it's going to lead to a lot of individual queries and going to slow you down. However, if you have too many group-bys, your intermediate result size is going to become very large, and that is going to hurt performance. If you think about it, the number of groups is essentially the product of the number of distinct values per attribute. And that sort of gives us a hint into a smarter thing that we could do. You can model this problem as bin packing, where the bin volume is the log of the maximum number of groups. The volume of each item is the log of the distinct values for that attribute. And you can apply normal bin packing techniques to find the optimal combination of groups. The great thing is this can be done offline because the combination of groups and the number of distinct values is not going to change a lot. OK, so this is what we're doing on the system side and on the runtime pruning. This is how we generally interleave the two optimizations. We run a bunch of queries on the database. We get estimates for utilities. We prune them. And based on the pruning, we run a subset of queries again on the database. And that's how we're combining what can be very disparate optimizations. OK, so this is all well and good. Does this actually work? Should anyone be looking at this? We looked at performance, latency, accuracy, tested it on various synthetic and real data sets. We're also doing a user study, so my focus will be more on qualitative rather than quantitative descriptors of how well we do. So this is how the pruning optimizations do. The x-axis shows how many of the top visualizations we're selecting. So are you selecting the top 1, the top 5, the top 20, and so on? And the way that we measure how well we do is by a metric called utility distance, which is what is the utility of the real top K visualizations, and what was the utility of the visualizations that SeeDB returned, and what was the difference between those two. As you can see here, the purple line is random. It does very, very poorly, as expected, because you're just selecting a random set of K visualizations. We find that both the confidence interval and the multi-arm bandit pruning techniques actually do very well with the utility distances being almost close to 0. They're actually just very close to 0 beyond 10. CI works a little bit differently from multi-arm bandit, so that's why you see a little bit of a bump around k equals 3 or 4, and I'm happy to talk offline about that. We also find that we see a significant reduction in latency if you use this pruning. So we can see that for k equals 1, we get a latency reduction of up to 90%. For k equals 10, which we think is a more realistic number, we get reduction of about 50%, which is very encouraging. So this is on the pruning side. We're throwing out a lot of visualizations that we don't think are good. But this is not going to do very much to get our latencies into the interactive timescales. And that's where the systems optimizations come in. I showed a similar graph before. This one shows what is the relative effect of applying all systems optimizations versus applying no systems optimizations. And we find that for a variety of data sets, we can reduce latency by up to 25x. We can get it into the range of tens of seconds, which is great. So putting it all together, you apply both of these types of optimizations on a variety of real data sets because the pruning techniques are really not applicable for synthetic data because they depend closely on data distribution. When you put both optimizations together, we find that SeeDB does quite well for small and medium-sized data. So for the bank, diabetes, and the airline delay data set, we can return results in a matter of seconds, which we think is a reasonable response time. However, if you go to a larger data set, which is 60 million rows and about 100 views, we are in the 20-second range, which is not acceptable. And for us, it is an area of future work. Currently, we don't do anything inside the database in order to speed up our queries. So looking at caching, indexing, and other techniques could certainly bring that down further. So that's on the performance side. We're doing interesting things to reduce latency. We're doing pruning without getting a significant hit in accuracy. But this is a tool that real people are going to use, real analysts are going to use. So we want to see how well we do. We're currently running a controlled experiment where the users use a manual chart construction tool, which is shown here. It lets them easily specify what charts to create, what x and y axes, and so on. We compare it to another tool, which is the same thing, except it allows you to get recommendations. And what that does is it populates a list of visualizations that the user might want to explore. So here are some user quotes. Again, this is very qualitative. We're still getting all the data, so hopefully we'll have concrete statistics soon. What we found is that people use SeeDB as a quick starting point. So if they were not very familiar with the data and wanted to get a quick overview of interesting trends, they found the recommendations very helpful. They also thought that SeeDB came up with some charts or trends that they wouldn't have thought of checking themselves, which again tells us that this tool can be useful. But we did find that when recommendations are available, people seem to lean on them a lot more than they should be, which means that we have a high threshold for the quality of these visualizations, and that's something that we need to factor in. Here are some very brief stats. All the users who did our study preferred the tool with recommendations. They thought that it sped up their analysis because they didn't have to construct the charts by hand. They could get a great overview of the data as well. 75% of them thought that the ratings were either helpful or extremely helpful, which was great because it told us that deviation-based metric might be a good way to go. We also find that users explore more views and more charts when we provide recommendations. Right now, this difference isn't statistically significant, but we find that about 1.5 times more charts are explored. Interestingly, the number of visualizations that users bookmark as interesting, so they say, I bookmark this because it shows me something interesting, was almost equal in the two settings. And we think that is because our current SeeDB prototype does not take context into account. So if someone is building a visualization, it's because they already think that it's interesting, and therefore they're more likely to bookmark it. And then finally, we found that expert users want sophisticated statistics. So show me error bars, show me outliers. Are these differences statistically significant, and so on? And that's something that we definitely want to incorporate. All right, so I talked about the evaluation both on the performance side and the user study. So that's the end of my talk, and I will summarize just briefly what we did. SeeDB is a visualization recommender. We developed a deviation-based utility metric. We came up with a few ways to prune the set of visualizations and speed up our analysis. We also found that users actually prefer having recommendations, and the kind of recommendations that we're doing are actually useful. Going forward, we will be incorporating other relevance metrics like context or other distance metrics that might be useful. And we think that this is a really promising area for research because users want such a tool that can get them quickly up to speed with a data set and point them to trends that they might want to follow up on. So that was SeeDB, and I'm happy to answer any questions.
Thank you very much.
Hi. Question related to why you chose this path as opposed to something else. And here's what that something else is in my mind. You take all the candidate attributes or features, and you run any feature selection algorithm that simply shows what are the interesting features, and then you visualize those features, as opposed to starting with something like you did.
Right. Could you talk a little bit about when you say feature selection, there's no training data that we have available here. So what sort of thing were you envisioning?
So, for example, in your graph about marital status, you had capital gain as your target, right? Mm-hmm. So in that case, that's a supervised feature selection with the capital gain as your target variable. So the feature selection would then pick interesting attributes for the capital gain as the target variable.
So is this, if I can paraphrase it, it's like you want to build maybe a classification model of some kind, and you look at the weights that are assigned to features? Is that?
Correct. So
okay.
You can build it using any, model building techniques, and then, but essentially, what comes out is the importance of each attribute or feature for that particular target.
Right. So I think that is a valid and a potential way to go. For us, we chose to not do anything fancy. We didn't want to go down the feature selection route. Trying to use ML techniques to find interesting visualizations is actually a very interesting thing that we can do in the future. What we ended up doing for version 2 is that we let users pick the attributes that they're interested in, and that sort of that sort of tells us by default that they're interested in these 5 dimensions or these 5 measures. So in the future, it'll be great to incorporate something like feature selection or ranking features into this.